Hello class. In this short video, we will discuss about the concept of power supplies and how the diodes can be used as a rectifiers. So before we start the lecture, we're going to just recap the last class. So the diode will conduct only when it is in the forward bias. Remember that this is the anode of the diode and this is the cathode. A diode can be forward biased if the voltage at the anode, so for example, voltage at the, let's say if you apply 5 volts and have a 1 kilo ohm load, so this is the load resistor which draws the current from the source. So in this case the diode is forward biased. So if I measure the voltage across this load using the multimeter, I will see 4.3 volts because the diode is forward biased, so it will take away 0.7 volts, which is the breakdown voltage of the diode. If the diode was reversed, then it is going to be in the reverse bias condition. That means, so I have the same source, but I reverse the direction of the diode. So in this case, I connected the positive of the source to the cathode of the diode. So in this case, the diode is reverse biased and the voltage across the load resistor is going to be approximately 0 volts because no current flows through the circuit because of the reverse biased diode. So this concept we talk about using the DC sources. So this one is a DC power supply or a DC source. So the same 0.7 volts will stand true even though we replace this DC voltage source with an AC voltage source. So in today's class, the applications AC analysis of a diode. So we're gonna start with power supply. So power supply is one of the major application that uses a diode in the rectifier stage. Major electronic devices will require a power supply which will convert a AC voltage source into a constant DC voltage source. So it is going to be used by a lot of consumer electronics such as televisions, computers, DVD players, and industrial control systems. So there are a lot of applications for this DC power supply. For example, if you consider your laptop battery charger or your mobile phone charger, that is a power supply. You plug in into the AC outlet and you will get a DC. So if you look at your battery charger, you will see the specifications typed on the power supply, how much amount of voltage it can give, for example, 12 volts DC, and also its ampere rating as well. A basic power supply will involves 4 major circuits, starting with transformer, which is going to be used to step down to a lower AC voltage. So for example, I have this AC line which is running at 120 volts AC and a 60 hertz signal. So because it's a very high voltage, let's say for example, you are expecting a 12 volts DC off of this power supply. So the very first stage is this AC signal is going to feed through the transformer. So in this case, this transformer is going to be a step down transformer. A step down transformer is nothing but it will convert this 120 volts AC, for example, maybe 20 volts AC. So that's the first stage of a DC power supply is a transformer used to step down to a lower voltage. The output voltage still looks like a sine wave with a 60 hertz, but the only difference is you will see that the voltage levels are going to be reduced. So in this case, maybe it's a 120 volts signal passed through a transformer, which is a step down transformer, and the voltage is going to be reduced but still carrying the same shape and same frequency. If it is a 60 hertz signal in here, and this is going to be 60 hertz, except it's a 120 volts AC, and maybe here it's going to be 20 volts. So we can change the secondary voltage. So we can change this voltage based upon the windings. So we will talk about the step down transformer before we get into the rectifiers. Next, after the signal is stepped down, the AC signal will pass through a rectifier. The job of this rectifier is convert this AC input signal which obtained from this transformer into a pulsating DC signal. Once the AC signal is passed through a transformer, now we have this low voltage AC signal. This will pass through a stage, it's called as a rectifier. So the job of the rectifier is convert this AC signal into something like that. So it's basically this rectifier is completely eliminating the negative cycle of the sine wave. So that's the second stage of the power supply is a rectifier stage. Once the signal passed through the rectifier, as you can see from here, this rectified signal is not a DC signal. Remember, the DC signal is a constant signal, so which looks like this. So no matter what, the level of the voltage is going to be constant with respect to the time. So after that, this rectified signal will pass through a filter which eliminates these fluctuations. So for example, this signal is going to passes through a filter, so that will generate this type of signal. As you can see, there are some ripples in this signal. This is not a completely DC signal that we are trying to generate. So this is how a DC signal is going to look like, a straight line. So the final stage of the power supply will include a voltage regulator, which will remove any variations. So for example, this signal will pass through the voltage regulator, so that will gives you almost a DC signal. And again, there is no circuit is ideal or perfect in nature. Even though the signal is passed through this voltage regulator, you will still see some voltage fluctuations. So that's what a DC power supply consists of, which is going to be a wall outlet, a 120 volts AC signal, which is passed through a transformer, which is going to step down the signal. Let's say, for example, in this case, maybe I'm going to consider it as a 20 volts AC. And then this signal is going to pass through a rectifier, which is going to remove one half of the AC signal. This rectified signal will pass through a filter stage, and once the signal passes through the filter stage, that signal is going to pass through the voltage regulator. So this is the transformer stage. So this is the rectifier stage. Here, once the rectified signal passed through the filter, and once the signal is filtered out, it is passed through the regulator. So these four are the major and very basic components of a DC power supply: a transformer, rectifier, regulator, and a filter. In this tutorial, we will talk about transformer and a rectifier. So how to use this transformer in order to step down the voltage. So once we step it down, we will talk about the concept of rectification. There are various types of rectifiers available: half wave and full wave rectifiers. So let's start with transformer. A transformer is used to couple the AC signal. There are two various types of transformers. One is the step up transformer and another one is the step down transformer. So step up transformer is going to be used to increase the voltage, and step down transformer is going to be used to reduce the voltage. In this particular application as a DC power supply, we will use a step down transformer. So there are two advantages of these two transformers. One is step up or step down, but in this case we're going to talk about step down. And another advantage is to isolate the AC source from the rectifier. So we can cause an electrical isolation. As you can see, transformers are based upon the inductors. So this is how the symbol of a transformer is going to look like. The lines in between the transformer will be the core material used. So that's the core of the transformer, which is in this case two parallel lines indicates that's the ferrite core. This side of the transformer is called as the primary side. This side of the transformer is going to be identified as the secondary side of the transformer. So here you can see that this transformer has two windings. One is the primary side winding, which is this one, and the secondary side winding. And these windings, or the number of turns that these windings could be different based upon whether you want to achieve a step up or a step down. Remember that step up is it will increases the secondary voltage. Step down is it will reduces the secondary voltage. So let's look at how it will step up or step down. It will be based upon the turns ratio. So the number of windings on the primary side and the number of windings on the secondary side, which is going to be calculated as the ratio of the secondary side over the primary side. Let's say, for example, I have a 120 volts AC signal applied on the primary side, and this transformer having a turns ratio of 2:1. So the secondary voltage of the transformer is going to be calculated as the primary voltage multiplied by the secondary terms, which is the 1 divided by the primary terms. So in this case, 1 divided by 2. So it's a 120 over 2, so the secondary voltage is 60 volts AC. So so in this case, this particular transformer having a turns ratio of 2:1 is going to step down the AC signal from 120 volts AC into a 60 volts AC. So by changing these turns ratios, we can generate a different value of the secondary voltage. Let's say, for example, here we are asked to find out the secondary voltage of this transformer having a turns ratio of 1:2. So the secondary voltage is nothing but the primary voltage, which is 120 volts, times 2 over 1. So remember that this ratio is the secondary turns over the primary turns. So in this case, 120 times 2 is a 240 volts AC. So this transformer is a step up transformer because it is converting 120 volts into a 240 volts. So lower voltage into a higher voltage. Alright, so this is the formula used for it. So the secondary side voltage is nothing but the primary side multiplied by the turns ratio, which is the secondary side over the primary side. Alright, let's look at this following example. It's asking calculate the peak output voltage of the transformer. So let us assume this 120 volts AC is going to be an RMS value, and it is going to be in RMS. The voltage coming out of the wall outlets is an RMS value, but in this case it is asking for the peak output voltage, which is going to be on the secondary side. So first of all, let us find out what this secondary voltage is. So the secondary voltage is the primary voltage times 1 over 10. Remember that it's a secondary windings over the primary, so it's a 1 divided by 10. So in this case it's going to be 12 volts, but this is going to be an RMS value because remember the input voltage, the primary side is an RMS. But the problem is asking to find out the peak output voltage. So we need to convert this RMS value into a peak value. So the peak secondary voltage is nothing but, remember, you need to take this RMS value and divide it by 0.707 in order to get the peak value. So you take the RMS value and divide it by 0.707. That will gives you 16.97 volts peak as a peak output voltage of this transformer on the secondary side. So here we first of all find what is the secondary voltage, and then we convert it into peak value because the problem is asking for the peak secondary voltage. Alright, so that's how we find out the output voltage of a transformer. We know the primary side. The second stage of this power supply is going to be the rectifier stage. So once the AC outlet signal will pass through the transformer, it will step down into a lower voltage value, and then that signal is going to be passed through a stage called as a rectifier. As we know, the diodes will conduct the current in only one direction, whereas they will block the current when they are reverse bias. So this is the same thing works even the input signal is going to be an AC signal. So rectifiers are used to convert an AC voltage into a DC voltage. Remember that the output of the transformer is going to be still an AC signal. It is not a DC signal yet. There are two categories of rectifiers: half wave rectifier and full wave rectifier. So let's talk about this half wave rectifier. So this is the circuit diagram of an half wave rectifier. The AC signal will pass through a diode, and then you have the load resistor, whichever. So the half wave rectifier uses the ability of the silicon diode to conduct the current when it is in the forward bias and inhibits the current when it is in reverse bias. For example, remember the fact here the input voltage is an AC voltage that is passing through the diode, and here you have a load resistor. So I have an AC signal, positive and negative cycles is passing through a diode. During the positive half cycle, so that means when the signal is greater than 0, so that's a positive and negative. Let's put the direction of the diode. That's going to be an anode, and this is going to be the cathode of the diode. So this is the cathode and that's the anode. So during the positive half cycle, let's say for example the input voltage you apply is 5 volts peak. So that means that's a 5 volts, and this one is a negative 5 volts. So during the positive half cycle, as the input signal going from 0 to 5 volts, again remember this is a silicon based diode, so you need to overcome the barrier potential or the forward voltage drop of the diode. If it is a silicon, it is 0.7 volts. So meaning that as the input signal is going from 0 to 5, if it is less than 0.7, the diode is still not going to be conducting because you need to overcome 0.7 volts. So the diode starts conducting above 0.7 volts. So as soon as it hits the 0.7 volts of the barrier, so let's say for example that's a 0.7 volts, then you're going to see the positive half cycle because 0.7 volts to 4.3 volts, so meaning that the voltage across that load resistor is going to be only 4.3 volts peak. So that's the maximum voltage you can give by removing the 0.7 volts of the forward biased diode voltage drop. During the negative cycle, again, negative cycle referring to the voltage is changing its polarity, the current is changing its direction. So that means during the negative cycle, this is what is happening. A negative voltage is being applied, meaning that the current is changing its direction. So a negative to the positive side or anode, that means the diode will be reverse biased. Remember that if you're applying a negative potential across anode and cathode, the diode will be reverse biased. So when the diode is reverse biased, the current is going to be zero. So the voltage across the load resistor is going to be zero. Again, remember that this is an AC cycle. The cycles keep continuing. So when the signal is coming back to the positive, again, the diode will conduct. When it is going to the negative cycle, it won't conduct. The maximum peak voltage across the load resistor is going to be 4.3 volts. When the input goes positive, the diode becomes forward bias and conducts the current through the load resistor, because you have here the positive is connected to the anode of the diode. So that means the voltage at the anode is greater than the voltage at the cathode. Then the diode is forward biased. So forward bias means it will allow the current. So in this case, there is going to be some current through the load resistor. So the current produces an output voltage across the load resistor, which is same as the positive half cycle. When the input goes negative during the second half cycle, the diode reverse biases automatically because you are applying a negative voltage across the diode. So the voltage across the load resistor, when it is reverse biased, there is no current in the circuit. When there is no current, there is no voltage drop across the load resistor. So that's going to be 0 volts. So the final voltage is going to be only the positive half cycle of the input voltage, and the output of the rectifier has its name called as pulsating DC voltage. So the average output voltage is going to be the peak voltage over the pi. Remember, it's a pi radians. So the diode is only conducting 180 degrees of the input cycles. The output average voltage, so if the problem is asking for an average voltage, it is going to be the peak voltage over pi, which is 3.14. So let's say, for example, I have a 120 volts AC signal applied to a transformer, primary side, and I have a secondary side of the transformer. Let's say, for example, I have a turns ratio of 10:1. So this is passed through a single diode, and I have a load resistor in here of 1 kilo ohm. So let's say the problem is asking for what is the peak output voltage across the load resistor. As you can see that this circuit is a half-wave rectified circuit using a transformer coupling having a turns ratio of 10:1. So first of all, we need to find out the secondary voltage. If you observe that the secondary voltage is fed to the rectifier, not the primary. So the secondary voltage is the primary voltage, which is 120 volts AC times 1 over 10. So in this case, it's a 12 volts. Remember the fact that this AC voltage, let's say it is given in RMS. So the secondary voltage is 12 volts RMS. But the problem is asking for calculate the peak voltage. So we need to find out the peak voltage of the transformer. So the peak secondary, which is 12 over 0.707, it will give you 16.97 volts peak across this transformer secondary. So here across this transformer we have 16.97 volts peak. So this signal is passed through the diode. So that means the voltage across the load resistor is 16.97 minus there is going to be a diode drop of 0.7. So what we have here is 16.97 minus 0.7 volts. So that will gives you 16.27 across the load resistor. So that's what we did here. So for practical diodes, you need to subtract 0.7 volts, but always remember that you need to work with the peak voltages, not the RMS voltages. So meaning that whenever you see an RMS, it's better to convert into a peak. So for silicon based diodes, we need to consider that 0.7. If it is a germanium based, it's a 0.3. During the positive half cycle, the input voltage must overcome the barrier potential. So the result peak value of the output voltage is 0.7 volts less than the input. Let's say, for example, we reverse the direction of the diode. So in this case, we connected cathode and anode. So in this case, what is the expected output voltage? So what is the output voltage if the diode is reversed? So that's what we have here. If you observe the direction of the diode right there and the direction of diode right here, which are exactly opposite to each other. So what is the expected output voltage here? So in this case, the output voltage will be exactly opposite to the previous one. In the previous case, the diode forward bias during the positive cycle, but in this case, it will be forward bias during the negative cycle. So this is the input signal. Let's say that's a sine wave. So if I were to draw the output voltage, so during the positive half cycle, so remember that here I have cathode, that's a negative, anode, that's a positive. So during the positive half cycle, I have positive to the negative connection. So that means the diode will be reverse bias. So when the diode is reverse bias, there is not going to be any current during the positive half cycle. So wherever I see the positive half cycle, that means there is no current. During the negative half cycle, I have a negative connected to the negative, that makes the diode forward bias. So what I'm going to see is whatever the input half cycle, and again remember here you need to subtract 0.7 because during the negative half cycle the diode is forward bias. So as long as the diode is forward bias, you need to subtract the 0.7 volts of barrier potential. So peak inverse voltage. As we learned from the last class, when the diode is reverse bias, it acts as an open circuit, meaning that the whole source voltage will be appeared across the diode. In the data sheet of 1N4000, we saw that the diode should withstand 50 volts. It stands true even the signal is an AC signal. When the diode is reverse biased, it must withstand whatever the voltage appearing across the diode because it will make the diode as an open circuit. So the PIV rating of a diode, which is exactly the same as that one, is the maximum voltage that the diode can withstand when it is blocking the current, which will happen when it is in the reverse bias condition, which is also called as peak reverse voltage, which is the maximum voltage that the diode can withstand in the reverse bias condition without breaking down or burning down the device. In a half-wave rectifier, the PIV rating is whatever the peak input voltage to the diode is. So for example, in this case, if I consider this example, the PIV rating of this diode is nothing but, because the diode is experiencing in here not this 120 volts in RMS, the diode is experiencing this 16.97 volts because that is the input voltage to the diode, which is nothing but the peak secondary voltage. And again, it's always going to be the peak voltage, not an RMS voltage. So that is the PIV rating of the diode, is the maximum voltage that the diode can withstand in the reverse bias condition. But in general, we always select the rated value must be at least 20% higher than the PIV. We don't want to operate the diode and its maximum ratings. Also in the previous example, we talked about the same half-wave rectifier. Again, here we are using only one diode for a half-wave rectification. So whenever you see a single diode, that rectifier is a half-wave rectifier. So as you can see, this half-wave rectifier is transformer coupled, meaning that the input signal is coupled through the transformer. So you need to first of all find the secondary voltage, and you need to subtract 0.7 from the secondary voltage. Again, we are talking about here all in the peaks. So this is the peak secondary voltage. Minus 0.7 will gives you the voltage across this load resistor. So that is the peak output voltage. And the PIV rating of the diode is nothing but this peak secondary voltage, whatever the secondary voltage is, because that's what is applying to the diode, not the V input voltage. V input voltage is applying to the primary side of the transformer, but the diode is getting the secondary voltage. So let's do this example. It's asking determine the peak value of the output voltage. So that means it is asking the peak output voltage cross this load resistor if the input voltage is 120 volts RMS and the turns ratio is given as 2:1, and it is also asking the PIV rating. So in this case, remember the fact that first you need to convert this 120 volts into its peak voltage. So you take the 120 and you divide it by 0.707. You can do immediately from the input side, or you could do the secondary side as well. So we have 169.73 volts peak, which is feeding into a 2:1 transformer. So in this case, we already converted into peak. So the peak secondary voltage is 169.73 multiplied by 1 over 2. So that means you are splitting this voltage into half. So that will gives you 84.86 volts peak. So that is the voltage that you are feeding to the diode for a half wave rectifier. But the peak voltage, peak output voltage is nothing but you take that 84.86 volts and you subtract, because when the diode is forward bias, you subtract that zero point 0.7 volts. So that will get you 84.16 volts peak. So this is the peak output voltage of the diode. 84.16 volts is the peak output voltage. And the PIV rating of the diode, remember that it is also asking the PIV rating. So the PIV rating of the diode is whatever the peak input voltage is to the diode. So in this case, the diode is receiving 84.86 volts peak. So that is the PIV rating of the diode. Thanks for watching. That will conclude this lecture.